الكل سامع الامور تمام بالصوت؟ ما اعرف انا.
ايوه الكل سامع.
طيب
اي واضح صوتك.
الله يعطيك العافيه. Okay. So start about what is the nuclear medicine. Simply, it's a medical specialty where a radioactive nuclide is attached to a pharmaceutical to study function of organs and organ system. So we are talking about functional imaging here. It's not mainly anatomical. So the functional imaging involves injecting a compound which is labeled with a gamma ray emitting for SPECT part or positron emitting radionuclide for PET imaging into the body. The radio-labeled compound is called radiopharmaceutical. We used to call it also tracer or radiotracer. Yes. Radiopharmaceutical is a radioactive compound used for the diagnosis and therapeutic treatment of human diseases. In nuclear medicine, we have almost 95% of radiopharmaceutical used are for diagnostic purposes. We have other 5% is for therapeutic treatment like iodine-131, lutetium-177, and yttrium-90 also included in nuclear medicine. A radiopharmaceutical may be a radioactive element such as xenon-133 or iodine-133, means that the element without any labeling is not attached to any compound. The radioactive element itself injected to the patient, or we can get a labeled compound such as a technetium labeled compound like technetium with MDB4 bone, technetium for another DTB for renal. So we attach compound to the radioactive for nuclear medicine imaging. The atomic nucleus is composed of a proton and neutrons. I know you know that, but just to review with you. And the proton and neutron inside the nucleus is called nucleons. This table gives the basic properties of nucleons and electrons. Here is the proton is +1, the charge, neutron is a neutral, has no charge, electron is -1, and we can see the mass of these like subatomic. It's like almost the proton and neutron have the same mass, and electron is less than, of course, it's very lighter. This U is atomic mass unit. And we can see here also the mass is in energy. So according to Einstein relativity equation here, we can see that energy and mass are interchangeable with each other. We can say that energy can convert it to mass and mass can convert it to energy. I need you to remember this one here, that this is very important, that electron and positron have this mass. And when this mass converted to energy, it will be equivalent to 511 keV or 0.511 MeV. Okay, this is important during annihilation. When we talk about annihilation, even in pair production is already reviewed before. That's why that when the electron or positron annihilate, it produce energy with 511 keV. Conversion factor between the atomic mass and energy, 1 atomic mass unit equal to 931.5 MeV. Nuclide is characterized by an exact number composition, including the mass number A, number of proton, and number of neutron should be identical, unique for each element. Atomic number, number of protons inside the nuclide, and also the arrangements of nucleons within the nucleus has specific arrangement for each element. To be classified as a nuclide, we can say this element is nuclide, or we can say radionuclide. Not all elements are radionuclide. So nuclide means that species must have measurably long, or we can say relatively measurably long existence, which for current technology means lifetime greater than about 10 to the power minus 12 seconds. This is long time for atomic, like subatomic mass. 10 to the power minus 12 seconds. Less than this one, we cannot say this is a nuclide. It is in excited state, we not consider it as nuclide. 10 to the power, it has life 10 to the power minus 12 and above, we can say this is nuclide. Some metastable states are quite long-lived, that is, they have average lifetime of several hours, like technetium metastable has 6 hours half-life. Because of this, metastable states are considered to have separate identities and are themselves classified as nuclide as well. So metastable, some of them are considered nuclide if they have average life above 10 to the power minus 12 seconds. These some radionuclides used in nuclear medicine, technetium-99, molybdenum, this is the generator. From the generator, we get the technetium-99 and other gallium-67, iodine-123. Iodine-131, it's used for therapeutic and for diagnostic as well. There are different types of nuclide. Let's start with isotopes. We keep saying radioisotopes in nuclear medicine. You can hear it very frequently there. So isotopes mean same number of proton or same atomic number Z. I remember that by looking at this like ball P here. Isotope, same number of protons from P, same protons with P. Just to remember that, same number of proton isotopes, different number of neutrons. When we say same number of protons, means same element. Always, if we have element with the same number of protons, we have the same element. Different number of protons, we have different elements. Like in isobar, we have same mass number A, same total number of nucleons, but distribution is different. Different number of proton, different number of neutron, but the total number of nucleons, the proton and the neutron inside the nucleus is the same. So, and it's the same thing. I remember that by A here, the bold A, this is like the same mass number A. Isotones, again here, N bold, same number of neutrons. The same number of neutron, different number of protons. So we are talking about different elements here and different elements here as well, because we have different number of protons. While in isotopes, we are talking about same element. Isomer E, but here is not the same energy. Here we talk about nuclides with different energy, like between the metastable and the stable, or the daughter of the metastable. So just a decay, and we're going to talk about it in the decay of more. Don't disturb you now. Okay, this is called isomer, include with different energy. Give you an example here that isotope, we see here the same element, iodine 127, 125, 131. These all are iodine because we have the same number of proton, and they called isotopes of iodine element. Isopar, we see here we have the same mass number and different number of Z, different number of N, different number of protons. But we have the same mass number, the total number of nucleons. Isotone, same number of neutron. We have here 10 neutron, 8 protons, 10 neutron, 9 protons, 10 neutron, and 10 protons. So different number of protons, but the same number of neutron, and we have, again, different elements because we have different protons. Isomer like technetium-99 metastable state are isomer. The technetium-99 metastable and the technetium-99, they are the same in everything except the energy state. This is in the metastable, this is in a, like in different state of energy. Let's talk about the forces within the nucleus. Nucleons within the nucleus are subject to two kinds of forces. The first one is the Coulomb force that repulses particles of like charge. We know that proton has positive charge and they are in nucleus. So we know that like charge repulse each other. So protons inside the nucleus have Coulomb forces that repulse each other inside the nucleus. There is another force called the very strong forces that binds the nucleons, protons and neutron together and overcome the Coulomb forces is called nuclear forces. So nuclear forces are effective only over very short distances, and their effects are seen only when nucleons are very close together as they are in the nucleus itself. So this is the condition that the nuclear forces affect only inside the nucleus and keep the proton and neutrons together. Nuclear forces hold the nucleus together against the repulsive Coulombic forces between the proton. So it is much stronger than the Coulombic forces that between the positive charge of protons. Binding energy, it's already covered in the previous lecture, but I will just cover it in the other part, like nuclear binding energy. I will just review it with you right now. So when the mass of an atom is compared with the sum of the masses of its individual components, like a proton, we take the mass of the atom itself, and we take the individual mass and sum it together, a proton plus a neutron mass plus electron. It all is found to be less by some amount, the mass of atom, less than the total mass of the individual or components of the atom. And this mass is called like deficiency mass, the difference in mass, called the mass deficiency. This mass deficiency expressed in energy unit is called the binding energy of the atom, which equals the mass deficiency multiplied by square of the speed of light. The binding energy is the minimum amount of energy required to overcome the forces holding the atom together to separate it completely into its individual component. Some of this represent the binding energy of orbital electrons. That is the energy required to strip the orbital electrons away from the nucleus. However, most of this energy is nuclear binding energy. That is the energy required to separate the nucleons, a proton or a neutron suddenly. So we have nuclear binding energy, and we have orbital or electronic binding energy. So electron binding energy related to photon interaction likelihood. The photon interact with the atom, take off the electron from the orbit, and after that, one electron jump to fill this vacancy and produce X-ray or OJ electron. So this is related to electron binding energy. Regarding nuclear binding energy, it is related to stability of radioactivity. More nuclear binding energy is more stability for the nucleus. Determine energy available following radioactive decay after decaying, the nucleus decaying to reach looking for stability. So electron binding energy, we can define it as energy required to fully remove an electron from an atom. I given here note that always greater than the energy required to bring the same electron to a higher energy state within the atom, an excited state. In excited state, the electron jumps from one energy state to another only, but the electron is still in the atom. But in binding energy, when we talk about binding energy, we are talking when the electron is removed from the energy required to fully remove the electron from the atom. This binding energy increases with the atomic number as z square. And we can see here like different element, increasing the z number or number of protons in the element, increase the binding energy. In K shell and L shell, we can see that K shell is more binding energy because it's closer to the nucleus. But the same principle that increasing Z will increase the binding energy in all shells. The nuclear binding energy, we can define it as energy required to fully separate individual nucleons from the nucleus. The greater the nuclear binding energy, the more stable the nucleus. So we're talking about the stability. So let's look at this plot here. This is a plot of nuclides found in nature according to their neutron and proton number. We can see here in the x-axis the number of neutrons. In the y-axis, we can see the number of protons. The line of stability here, the bold one here, divided the nuclides in a neutron deficiency in this region. Element in this region has a neutron deficiency, means the number of a proton here more than the number of a neutron. And also neutron excess or proton deficiency, number of a neutron in this area is more than number of a proton. The best stability is achieved when the number of protons and the neutrons in the nucleus is about the same, like we have 5 proton, 5 neutron, 10, 10. This is the best or ideal situation of stability. So from this plot, we can just we can see that light element here, this is light element, number of proton or a neutron increase, we get heavier elements. So lighter elements in this region, for light element, the stability line follows the straight line. We can see here, this is like same number of proton equals number of neutrons. Number of neutrons equals number of proton, means N equals Z. For heavier elements, there is a neutron excess. We can see by going for heavier elements, we have almost N here more than Z. So if we go for 8 here, 8 neutrons, we can it's about 60 or 70 protons. So we have excess in neutron for heavier element. This approximately 50% more in neutron than a proton for heavier elements. The neutron excess makes the Coulomb forces decrease in heavy elements. That's why we have more neutrons. More neutrons are needed to hold together larger number of protons, because in heavy elements, we have more number of protons, more Coulomb forces, more repulsive forces. That's why we need more neutron to overcome these forces, Coulomb forces, and get more nuclear forces. Any questions so far? Everything is okay with you? Okay, thank you. Last point here, okay. There's a question regarding the last point, could you repeat? I said that we have no audio.
احنا سامعين. ما ادري دكتورة أروى يمكن تحتاج تشوفين الاوديو سيستم عندك.
Okay, just repeat quickly that we say that the ideal situation that the proton is equal to number of neutron to get the stability. The nucleus is stable if the number of proton is equal to number of neutron. But in heavy elements, this is not the scenario, because we have more proton. More protons inside the nucleus mean more repulsive forces, because we have the same positive charge inside nucleus within very close area, very small area. So to overcome the repulsive forces of a proton, there are many neutrons. The number of neutrons are more than number of protons in the heavy elements just to overcome of repulsive forces. This is the nature. Like this is how we found the elements in the nature. So for uranium, for example, and these heavy elements, always the number of neutron more than the number of proton, just to keep the nucleus together, just to increase the nuclear forces. Usually remember, like for heavy element, about 50% more in neutron than in protons, and more in neutrons are needed to hold together a large number of protons. Okay. A nucleus not in its stable state, if it is like has more energy, unstable, will adjust itself until it is stable, either by ejecting a portion of its nucleus or by emitting energy in the form of photons. And energy from nucleus always gamma ray. This process is referred to radioactive decay. By the way, the difference between gamma ray and X-ray, you know that, just to remind you, that X-ray is coming out from the orbital of the atoms, orbital region of the atom, while the gamma ray is coming from the nucleus. Otherwise, it is electromagnetic waves, the same thing. Anyway, so we are talking about radioactive decay here. So unstable is trying to adjust itself just to be like more stable atom. So by ejecting like the component of the nucleus or ejecting gamma ray. So there are different decay modes, as we can see here. In different decay mode, either the atomic number decrease or atomic number increase or atomic number not increase at all by isomeric transition. We go by one now, just explain in more details. Radioactive decay It's a spontaneous transformation of unstable nucleus into a more stable one by emission of particles or photons, releasing energy in the process. The process is usually described using this equation, where the unstable radioactive nucleus is referred to as parent, and the more stable product nucleus is the daughter. And emissions, like whatever is emission, alpha, gamma, or, but here Q, what is a Q here? Okay, a Q is the transition energy. And where does this transition energy go? Shared between the daughter and various emissions. It could be kinetic energy for the emissions, could be whatever, like divided by the emission and the daughter. So this is called transition energy. I think it is already explained in the previous lectures. So unstable give more stable daughter, plus emissions, beta, alpha, gamma, whatever, plus the transition energy. The daughter can be in its ground state or still in the excited state. After radioactive decay, not necessarily to get to stability or to get to ground state. Still, maybe it is another excited state. And again, radioactive decay happen, go to another excited state, and so on until to reach to the stability. The main mode of decay, alpha, beta, gamma. We start with alpha decay. Alpha decay occurs in heavy elements because an alpha particle consists of 2 neutrons and 2 protons, and it's identical to a helium nucleus. Helium nucleus have 2 neutrons and 2 protons, and this is the alpha particle. And due to its large energy and highly positive charge, it can be of use for therapeutic purposes rather than for medical imaging. So we don't use alpha particle in medical imaging. It's only for therapeutic. Also for therapeutic, it's very limited because its range in tissue very, very limited. So we can see this one here, that this is the parent and decay by alpha particle, and the daughter will reduce, the number of A will be reduced by 4, and Z will reduce by 2, because we get here 2 proton, 2 neutrons, mean the number of neutrons will be 4, minus 4 of A and Z minus 2. And this is an example here of radium and radon. We can see that the atomic number is 226, we get 222, so minus 4 and 88 number of a proton get 86 of number of a proton and alpha particle. Okay, so the atomic number decreased by 2, the mass number decreased by 4. This is the alpha decay. This is the formula, and I would like you to give me what is Y here, what is A and what is Z. We have radon 222 decay by helium particle. So what is A and what is Z, please? Yes, I know, but the number, give me the number. Okay, you got it right. 218 and 84, minus 2 and minus 4. Excellent. So we'll go to beta decay. There are 2 types of beta decay. Beta minus and positron or beta plus. Beta decay is the most common of all decay modes and usually involves transition to an excited state resulting in further gamma photon emission. So like in this example, this xenon here, decay by beta, and after that, decay again by gamma to get to another like energy state. Again here, beta, then gamma. So it is like followed by gamma. Most of the beta decay is like behaving the same thing. Beta after that decaying by gamma, even for iodine 131. This is the most common isotopes for therapeutic and nuclear medicine. It has 2 decay, means that if we have iodine 131, we have the iodine 131, we expose to iodine 131 by beta and also by photon. So emit beta and photon at the same time. Beta emitting radionuclide that only decay directly to ground state of daughter are referred to pure beta emitter. There is no gamma with beta here, like in yttrium-90. Yttrium-90, pure beta emitter. It's like just decay by beta emitters and go to the ground state. Start with a beta minus decay. A neutron transformed into a proton and electron, or we can call the electron as beta here. So the neutron inside the nucleus, one neutron will be converted to proton, means the number of a neutron will be reduced, the number of a proton will be increased. But we're gonna have the same atomic number, okay? So the electron and the neutrino are ejected from the nucleus and carry away the energy released in the process as kinetic energy in this process. The electron is called beta particle. The neutrino is a particle having no mass or electrical charge. Okay, so the atomic number increased by 1 because 1 neutron will be converted to 1 protons, mean the number of Z will be increased by 1. But mass number stay the same because 1 neutron converted to 1 proton. Still, we are within the nucleons. We are talking that the nucleons is the same, or A is the number of a proton and a neutron. So we didn't change anything here. We just convert 1 neutron to proton. So the total is the same. So A is the same, Z plus 1. Okay. Again here, we have the thorium-234 decay by beta minus. So what is A and Z here? Excellent, you got it. Great. So the mass number is 234, same, and here plus 1, we get one more proton. The other kind of beta decay is positron decay or beta plus decay. The proton is transformed into a neutron here. And the beta minus neutron converted to proton. Here it's opposite. A proton transformed into neutrons, meaning that number of a proton decreased by 1 and A is still the same, okay? And positron and a neutrino is emitted. So unlike beta minus decay, in this one, another interaction always follows with positron decay. This is because a positron is an antiparticle. Positron has a plus, electron has minus charge. Positron has a plus particle, so it is attracted by other atoms. So within a very small distance, it will annihilate with an electron from other atom. Their mass is then converted into 2 annihilation photons, each with a kinetic energy of 511 keV. So this is what we talked about, like that positron and electron annihilate each other and their mass is converted to energy. So, and get 2 annihilation photons. Each annihilation photon has 511 keV. So this is positron meet electron, annihilate each other. The mass of positron and the mass of electron converted to energy and get 2 annihilation photon. Each one is 511 keV, mass converted to energy. These are emitted back to back, about 180 degrees between them from the site of annihilation. These photon use in PET imaging, we're going to discuss that during when we reach to the PET imaging representation. Anyway, so for positron decay, the atomic number decreases by 1 because 1 proton will be transformed to neutron and the mass number stay the same. Again, here for the boron 8, what is A and Z? Okay, excellent. So we have the same atomic number, same mass number, and minus 1 proton here, exactly 4. The next decay is electron capture. Orbital electrons is captured by the nucleus and combined with the proton to form an neutron and a neutrino. So electron from the orbit attracted by the nucleus, this electron like combines with the proton, and proton converted to a neutron. So we lose 1 proton here. 1 proton will be transformed to neutron after combining with a electron, orbital electron. Okay. The electron is usually from a lower K or L shell, which is like closer to nucleus. So the nucleus attracted usually the electron from the K shell. Again, a hole is left in the shell. Okay. So 1 electron from other energy state from the upper orbit jump to fill this vacancy, and the difference between the energy will be emitted as X-ray or OJ electron, as discussed in the previous presentation. So this kind of decay has, we have electron capture here, and we get 1 proton converted to neutron, and we get also X-ray. So we have iodine 1, it's most common iodine 123 in nuclear medicine, we use that. So the X-ray always contributed with the gamma ray emitted by this kind of element. So we have always X-ray and also gamma ray emitted from this kind of element. So in electron capture, the atomic number decreases by 1 and mass number stay the same. And if you see, this is the same scenario here. The atomic number decreases by 1 in the positron decay. The same thing, the atomic number decreases by 1 here, and the same. So electron capture almost give us the same result of positron emitters. So I need you also again here for electron capture, we have argon 37. What is A and Z here? So electron capture by argon, and we get this daughter. Great, excellent. We have 37 mass number and 17 for number for proton. As we said, there's a competitive between the positron and electron capture decay. Positron emission and electron capture have the same effect on the parent nucleus. Both isobaric decay modes that have the same mass number, but Z minus 1. Isobaric from, we remember the A, we are talking about a mass number. So they have the same, the daughter had the same A, but we have Z minus 1. The positron decay occurs more frequently among lighter elements, whereas the electron capture is more frequent among heavier elements. Because in heavy elements, orbital electrons tend to be closer to the nucleus and are more easily to capture. So positron, for the lighter elements, electron capture, this is most probably, that's not like a rule. Electron capture more frequent among heavier elements because the electron is closer to the nucleus than in the lighter elements. The next decay is the gamma decay. Gamma decay occurs when a nucleus in a higher energy state spontaneously jumps to a lower energy state. The result is emission of a very high frequency photon, or we can say gamma photon because it is from the nucleus. Decay of such nuclei by emission of the gamma photon known as an isomeric transition. Okay, there's no change in the proton, number of protons the same, number of neutrons the same, but only the energy state is changed. We have excited energy state here, metastable, and we get lower energy state plus gamma photon plus the transition energy. The Q here is the difference between the excited state and the next energy state, the difference between the two energy. The excitation energy originates from the nucleus. Technetium-99 metastable, it is the most popular radionuclide in nuclear medicine imaging. It is in this like decay in this process. It's isomeric transition. There is no change, as we said, in mass or atomic number. We have the same number of proton, same number of neutron, only energy state is changed during the isomeric transition. The next decay is internal conversion. It is alternative to gamma photon emission. Nucleus transfer excess energy to an orbital electron, okay, and electron known as a conversion electron, then ejected instead of gamma photon. Electron usually originate from inner shell, K or L. So the nucleus has excess energy. This excess energy transferred will usually emitted by gamma photon, but this energy transferred to electron in the orbital, and this electron takes this energy and ejected it from the atom. This electron ejected because of the excess energy from the nucleus called the conversion electron. Again, subsequent emission when vacancy left by eject electron, we get X-ray or J electron. Okay. Any question about that? Okay, thank you. So it was noted that on a graph of a neutron versus a proton, the stable nuclei tend to be clustered about the stability here. Okay, nuclei lying off the line of stability generally are radioactive. The nuclei that is within the stability line here clustered just to close. So sorry, there's a question here. What is the, you mean what is the relationship between the internal conversion and J electron? So I said that here, the conversion, the energy, sorry, I just go back just to answer the question. There's a question about that. So the excess energy in the nucleus converted to the electron from the orbit will be ejected from the atom. So we have vacancy here. And usually this vacancy filled by the other electron in the upper state. And the difference between the two orbits emitted by X-ray or could be OJ electron, like the same principle of X-ray. There's vacancy filled by another electron and the difference emitted by OJ or X-ray. This is the only relation, nothing else. Okay. Anyway, we say that, just to repeat here that, okay, the stable nuclei tend to be clustered about the stability line. Nuclei lying off the line of stability generally are radioactive. The type of radioactive decay that occurs usually is such as to move the nucleus closer to this line. The nuclide always tries to get to the stability line to be more stable. A radionuclide that is in a neutron axis side, in this location here, usually decay by beta minus because this transforms a neutron into proton, moving the nucleus closer to the stability or the line of stability. A neutron deficient radionuclide usually decay by electron capture or positron because these modes transform a proton into a neutron and move it closer to the line of stability. This is just summary of the emissions. We talk about alpha decay, loss of helium nucleus, mass number reduced by -4, atomic number reduced by -2. Beta minus, lose electron from the nucleus. There's no change in the mass number, and +1, number of proton is increased by 1. Electron capture and positron are the same, okay? A proton turns into neutron, and we get -1 of the atomic number, and there's no change in the mass number. The gamma decay, no change in the atomic number, no change in the mass number, emits high energy gamma ray. So let's have some question to just check your are following. Sorry. The mass number of an atom A is the number of what? A neutron in the nucleus, a proton in the nucleus, proton, electrons, and neutrons, proton, and neutrons. Yes, correct. D. Excellent. Electron binding energy depends on atomic number, atomic mass, or atomic size, or chemical binding. Electron binding energy. A, B, A. No, it depends on the atomic number. Okay. Number of protons. Elements which have the same Z atomic number but different A mass number are called same Z number. Isobar, isomers, isotones, or isotopes. Same number of a proton. You remember we said P. Okay, P is here, so we have D, isotope. Excellent. When cobalt 60 decays to nickel 60, which of the following is emitted? We have Z27, here the Z28. So number of proton increased by 1. So what we have here, positron, electrons, alpha particle, or X-ray? C, we talk about alpha particle is 2 proton, 2 neutron. You're gonna see like -2 proton. Here the number of proton increased by 1. Number of proton increase means the neutron converted to proton. Okay, excellent. Now we get it. Yes, it's beta decay. Beta decay or electrons, it's the same. Electrons called beta minus decay. In beta minus decay, a neutron in the nucleus is converted into a proton, and an energetic electron, beta particle, and antineutrino are emitted. So beta decay, electrons, 1 proton converted to neutron, so we get a plus 1 neutron converted to proton. So yes, we have 1 more proton. So electron capture can result in emission of antineutrino, neutrons, characteristic X-ray, or positron. Okay, Or C. Very good. Excellent. So the answer is C. As we said, that there is a vacancy filled by another electron and X-ray emitted after the transition of one electron to another state. Okay, this is the end of the first presentation. If you have any question, please let me know. Thank you. Energy, types of energy. Oh. Which slide? I'm a little bit confused. This one you mean, or? First slides. I mean, types of nuclides, we go. Just let me know which one. I don't see this one. Sorry,
تقصد the types of nuclei يا أستاذ محمد.
Type of nuclides?
Yes.
This one here?
هذه في ولا؟
Types of energy. I don't remember I get types of energy. I got radio.
تقصد الألفا والبيتا ولا؟
I just go through the slides if you find your slide. Okay, sorry, I couldn't get it. Okay, this another question. Electronic and nuclear binding.
هذا اللي تقصدها في أستاذ محمد.
Okay, binding energy. So there are, okay. We said there are nuclear forces inside the nucleus. There is column forces, repulsive forces between the protons, and there is strong forces called nuclear forces inside the nucleus. This is about the nuclear stability inside. Binding energy, there are two different binding energy. Binding energy, there's orbital binding energy. Okay, electron binding energy related to photon interaction likelihood, means like when the photon interact with the atom, okay, there is like minimum energy of this incident photon to remove the electron from its orbit. So this minimum energy required to remove the electron from the orbit is called the electronic or electron binding energy. This is the minimum energy required to remove the electron from its orbit. So because the electron is binding, means like it is just what يعني belongs to this orbit. Okay, to remove this electron from its orbit, you have to have minimum energy to remove it. Already explained by Ms. Maram in the first presentation, I remember. There's another kind of binding energy is called nuclear binding energy. And this is related to the stability of radioactivity, how the nucleus hold the components of the nucleus together, how the nucleons together, and this nuclear binding energy related to the forces inside the nucleus, inside this one, the nuclear forces and the repulsive forces, okay? The nuclear binding energy, how to keep, here's the nuclear binding energy, energy required to fully separate individual nucleons from the nucleus. So to take off or to remove one of the component of the nucleus, you need minimum energy to do that, okay? To overcome the binding energy of the nucleus. Energy required to fully separate individual nucleons from the nucleus. This is the binding energy, okay? The greater the nuclear binding energy, the more stable, because it's gonna be more stronger. If we have more nuclear energy, the stability is more, and the nucleons are very stable inside. You need more energy just to remove the nucleons from the nucleus. I'm not sure if you got it or not. Thank you. Any other question, or shall we go to part 2 of the presentation? For sure, I will send you the soft copy of presentation.
بنرسلها إن شاء الله الليلة بإذن الله.
Inshallah. Okay.
Awesome. We can proceed to the next presentation.
Okay, so let me just transfer. Okay, this is the part 2 of the basic physics of nuclear medicine. And in this presentation, I'm going to cover the radioactive decay, activity, and radionuclide production. And the reference in the same book here, the Sorensen book, chapter 4 and 5. Radioactive decay is a spontaneous process which transforms a nucleus from an unstable to stable or more stable, not necessary to be stable or more stable than the parent. Radioactive decay is a random statistical process. That is, there is no way to predict with certainty the exact moment at which an unstable nucleus will undergo its radioactive transformation into another more stable nucleus. It is a random process. Although it is a random statistical process, the rate of decay for a given isotope can be quantified using the exponential equation here. Herein, we can see is the number of atoms at any time with relation to the number of atoms initially present multiplied by a decay factor, E minus delta lambda T. This expression is called a decay factor, which comprises of a decay constant and time. The decay constant lambda and decay factor is the probability that an atom will decay in a given unit of time. So this gives us the probability when the atom will decay. Unique, its lambda is unique for each radionuclide and doesn't change. It's like in its identity. Lambda for this element is fixed, the same like half-life and other characteristic of element. Standard unit are inverse second or inverse time. So 1/2, the unit of the lambda. Inverse of lambda is known as the average lifetime of atoms in a sample and has unit of time. For sure, it is inverse of lambda, so the unit will be time. This is the inverse time. So the unit of the average lifetime, it's unit of time, could be second, minute, whatever. More useful concept is that of half-life. Half-life, it is time taken for the half of the sample to decay. Half number of the sample, the number, we have an element, have atoms, half of this atom will decay within this half-life. So the half-life equal the ln2, this is natural algorithm, ln2, which equal 0.693 divided by lambda, which is the decay constant. Half-life, we have physical half-life and we have biological half-life, and the relationship between the physical half-life and biological half-life can be calculated by effective half-life. Physical half-life is the time taken for half of the atoms in a radioactive material to undergo decay. The physical half-life of an isotope is related to the decay constant, the probability. It is characteristics for every radionuclide. So for example, half-life of technetium-99 metastable is 6 hours. It is always 6 hours. Either it is inside the body, outside the body, whatever, the 6 hours is fixed for this kind of radionuclide. So it doesn't change, the same like the gamma constant. While biological half-life is changeable, the time taken for the half of the atom to be naturally removed from the living tissue, example, excretion in urine. So we inject the patient with radionuclide, could be iodine-131. We give capsule iodine-131 for radioiodine therapy. The half-life of iodine-131 is 8 days. So, the decay should happen as physical half-life after 8 days. But when we come to the patient after 3 days, we almost find nothing, like we couldn't find any activity inside the body because of biological half-life, because most of the iodine-131 goes out of the body through the urine. So we don't rely only in the physical half-life in nuclear medicine. Also, we calculate the biological half-life because the biological half-life depends on the distribution of radioactivity inside the body. Also, the uptake of the organ. So from one organ to another organ, the uptake is different. And the time that the radionuclide stay in the body is different from one organ to another, from one radioactive to another radioactive. So biological half-life, it gives approximately 4 different organs. And to calculate the effective half-life, to calculate for how long this radionuclide will stay or remain inside the patient body, we calculate the effective half-life, not only the physical half-life. We said, okay, we have iodine-131, the biological half-life of iodine-131 inside the body, it's like this. And we have the physical half-life and calculated by taking the multiplication of physical half-life and biological half-life divided by their summation, physical half-life plus biological half-life. The same expression, but different arrangement. I like this one. It's easy to remember. The multiplication of half-life, biological and physical over the summation of the half-lives. Okay, and you can see this is the half-life degree. We can see after one half-life, this is one half-life, the activity is, or the number of atoms to get half. After 2 half-life, the number of, the activity or the number of atoms go quarter, and so on. This is the curve of the half-life. Average lifetime, tau B, of radioactive parent P is the time during which the number of radioactive parent nuclei, the number of atoms of the parent, falls to the 36.8% of the initial number. So when the number of parent decay and reach to the 36.8% of the initial number of atoms, this is called the average lifetime. Okay, and if we calculate that, we know that lambda equal, we say T half equal ln over lambda. So lambda equal ln2 over T half. This is the how to calculate the decay constant. Ln2 over T half. We are talking about the parent here, so I put P here. And ln2 is 0.693 over the T half of the parent. So just rearrange that one. Lambda P we say it is you remember we say the average lifetime is the inverse of lambda, and lambda is the inverse of life. And this in the slides here, we say that inverse of lambda is known as the average of lifetime. So these are inverse each other. So lambda is equal 1 over tau, the average lifetime. So tau, if we need to calculate tau, the average lifetime, it is the half-life. We just inverse this one, half-life over ln 2 and equal 1.44 t-half. This is just to show you that the average lifetime for the atom of a radionuclide is therefore longer than the half-life by a factor 1.44. The concept of average lifetime is very important in radiation dosimetry calculation. When we do the dosimetry for the patient, we use this, the average lifetime. So the average lifetime is longer than half-life by a factor of 1.44. Let's talk about the activity now. It's difficult to measure number of atoms directly, so we cannot say how many atoms decay per time. So we cannot count the atoms, how many atoms. So it's easy for us to directly, it's useful to quantify the rate of a transformation or rate of decay, also known as activity. The rate of a transformation is known as activity of the sample, as this can be measured by detecting the emission. So we can get it even by taking like survey meter or monitoring it. We can get the activity, or we can measure it in the radionuclide dose calibrator. So we can get the activity, how much activity initially, how much activity afterward. It can be easily measured. Not easily, but it can be measured, means in the instrumentation. But to get how many counts, how many atoms, is very difficult to get this, how many atoms decay. So it's easy to express that by activity. Activity almost the same of, if you look at the equation here of N, and it is the same, N naught E minus lambda T, we get the same here for activity. Activity at any time equal activity, initial activity multiplied by the decay factor E minus lambda T. So either way, you can calculate the decay of the atom. Equations for activity calculation, we can get this one. The A naught is the initial activity. The final activity equal the initial activity multiplied by the decay factor. So, you know, the activity means that when we go to the patient, like we need to give the patient dose, you say, okay, we give him, for example, 4 millicurie. This is the activity, 4 millicurie. This is the dose given to the patient, 4 millicurie. Okay, so to calculate that, okay, we have 4 millicurie now. After 6 hours, it's gonna be 2 millicurie for technetium. So this is the final, 2 millicurie is the final activity. 4 millicurie is the initial activity. After half-life, it's gonna be like this much of activity. We're going to explain that through the examples and other slides. Now it's coming. So to calculate the final activity equal initial activity multiplied by decay factor, or we can just rearrange this one to get this equation here, -6, this is ln 2 over t half multiplied by the time, because we know that lambda equal ln 2 over t half. So we just convert the lambda to 0.693 over t half multiplied by the time, or we can say that, or we can arrange it in this way. The A naught is 2 because the exponential of 0.693 is equal to 2, and we just keep this expression here. So whatever you need, you can use any equation to calculate the activity. These equations are applicable for one parent nuclide and one daughter nuclide. We cannot use it for mixed radioactive. Sometimes we have mixed radionuclide together, many parent and many daughters, so we cannot use this equation for multi-radionuclides mixed together. This is only for one parent and one daughter. So the question, can daughter nuclide be radioactive too? We said that yes, it can be radioactive and decay another time and another time. The unit of activity is curie. This is the most common, like we use here in Saudi Arabia. A curie named after Marie Curie. A curie is roughly the activity of 1 gram of isotopes of radium-226. The international unit of the activity is becquerel, named after Anthony Becquerel. The 1 becquerel means 1 disintegration per second, 1 decay per second. Okay, this is 1 becquerel. And as we said, in Saudi Arabia, for example, we use curie. In Canada, they use becquerel, and different countries use different units. The conversion in between the curie and becquerel, 1 becquerel, we said it is equals to 1 disintegration per second. 1 curie equal to 3.7 to the power 10 disintegration per second. So I usually remember 2 things, and then I start conversion. So I remember this one, 1 millicurie equal to 37 megabecquerel, and I remember this one, 1 gigabecquerel equal to 27 millicurie. Then I start converge. If I have micro, tera, it's easy. Just remember 2 of them, or 1 or 2 of them, and it will be easy for you to convert the others, the other numbers. I give you example here. So we have vial of technetium-99. The half-life of technetium-99 is 6 hours. Activity at 8 a.m. is 6 gigabecquerel, and this activity, it is in the volume of 6 ml. So the volume 6 ml, inside this 6 ml, we have 6 gigabecquerel. At 10 a.m. means after 2 hours, you want to give patient 5 megabecquerel, 500 megabecquerel. What volume do you want to inject? Okay, this is every day in the hot lab in the nuclear medicine. So the technologists in the hot lab start calculating. They said, okay, this patient get 500 megabecquerel. I have this amount of activity. I have this volume. How much volume I need to give? It's easy to just to withdraw the volume, then measure it, just to confirm the activity inside the volume. But too easy to handle the activity, it's good to know the volume. So this is at 10 a.m. we calculate the activity. So at 8 a.m. the activity was 6 gigabecquerel. So this is the initial activity here, 6, and we need the final activity A. Okay, lambda, we know it's ln2 over t half, this one here. We have the t half is 6 hour, ln2 0.693. Okay, so to calculate the activity, we have 6, the initial activity, and we have ln2 multiplied by 6, divided by 6, this is the half-life, multiplied by 2, this is 2 hours difference between 8 and 10. And we get the final activity, it's 4.76. So at 10 o'clock, the activity from 6 became 4.76. Okay, now concentration, we have 4.76 in 6 ml. So in each ml, we divided this one on 6. We get in each ml, we have 790 megabecquerel. Okay, so I need 500. So I need divide 500 over 790 megabecquerel. I need to withdraw 0.63 ml. Inside, within this 0.63 ml, we will get 500 megabecquerel. But for sure, we go to dose calibrator and we measure our dose, because this is estimation. Then we go and just to confirm our dose. But this is what is every day done. Like for each patient in nuclear medicine, the technologists do that, but in a quick manner. The specific activity, let's talk about it now. This important term also in nuclear medicine. A radioactive sample may contain stable isotopes of the element represented by the radionuclide of interest. For example, a given iodine-131 sample may also contain the stable isotope iodine-127. So we have radioisotopes, radioactive material, and within this radioactive material, we have also stable. Okay, so we don't need stable elements or stable nuclide inside the radioactive material injected to the patient. This is for useless. When stable isotopes of the radionuclide of interest are present in the sample, they are called carrier. And the sample that does not contain stable isotopes of the element represented by their radionuclide is called carrier-free. Radionuclides may be produced carrier-free or with carrier, depending on the production method. Okay? The ratio of radioisotope activity to total mass of the element present is called the specific activity of the sample. So it is the ratio of radioisotope activity to the total mass of the element, and this is the definition of the specific activity. A more complicated situation occurs when a sample contains radionuclides having parent-daughter relationship. In 1910, mathematician Harry Bateman, this guy, solved the system of differential equation which describe radioactive decay. So the Bateman equation of parent-daughter mixture, so this is the activity of the daughter, this is the daughter parent, and this daughter parent has a relationship, okay, parent-daughter relationship inside the sample. And we can see here, this is the activity of the parent, and this is the decay constant of the parent and daughter, multiplied by the decay factor of parent and daughter, and this is the branching ratio. And so this is long equation and complicated one. This equation for the activity of a daughter is complicated by the fact that the daughter product being formed by decay of the parent, and at the same time it is decaying. So daughter is creating by the parent is decaying, parent is decaying, so daughter is creating. And at the same time, the daughter is decaying as well. So it is very complicated. But don't worry, you don't need to know this equation. It just show it to you just to see that it is a complicated situation. But what I need you to remember that these the three equilibrium states. The Bateman equation for a parent-daughter mixture can be analyzed for three general situations based on a comparison of the decay constants: secular equilibrium, transient equilibrium, and no equilibrium. We'll go one by one now. This is the secular equilibrium. Secular equilibrium arises when the parent half-life, this is the parent activity and this is the daughter activity. When the parent half-life is so long that its decay is negligible over the observation period while the daughter activity builds up. Parent activity is very, very high, like very long. Okay, longer than the daughter activity. So while the daughter activity builds up here, you see here, this is the parent is decaying. After about 5 half-life of the daughter, the activity of the daughter will be equal of the parent. We can see here, okay? After, this is the half-life of the daughter. After 5 half-life, we see the activity of the daughter now starting like decaying with the parent together. When this occurs, I mean that when the activity of the daughter equal the activity of the parent, okay, and daughter are said to be in secular equilibrium. When these activity are matched together, the activity of the daughter and the activity of the parent, we can see the parent and daughter are in secular equilibrium. And the good example of this one is the rubidium-81. The half-life is 4.6 hours, while the daughter is the krypton-81. The half-life is only 13 seconds. Another example is radium-226. The half-life is 1620 years, while the daughter is the radon 4.8 days. I know it's not easy to understand that way, but I want just to know that the parent has very long half-life, the daughter has very shorter means very like big difference between the parent half-life and the daughter half-life. The parent is decaying, the daughter is built up. When the daughter reaches to the activity, the same to the parent activity after about 5 half-life, we say that they are in the secular equilibrium. A transient equilibrium arises when the parent half-life is only about 10 times longer than the daughter half-life. Here, the daughter activity builds, then decay at the same rate as the parent, okay? When parent and daughter activities are decreasing, but the ratio, you can see here, the ratio of the parent to daughter activity are constant. There is no change between the two, like that we have the same ratio all the way. Okay, we can say that the parent and daughter are in a transient equilibrium. Again, the parent decaying, daughter builds up, because parent, when the parent is decaying means that creating the daughter. Parent decaying, the daughter is built up. Okay, and reach to when the activity of the daughter and parent decaying together with the same rate, same ratio, without any change, we say they are in the secular equilibrium. Okay, the most commonly used nuclear medicine technetium-99 daughter is type of this decay chain. We can see that the parent of the technetium-99 is molybdenum-99. The half-life of molybdenum-99 is 67 hours. And the half-life of the technetium, the daughter, is 6 hours. We can see almost 10 times, sorry. The half-life of the parent, it's greater than this one, about 10 times. So this is the example of the called transient equilibrium. Finally, a situation of no equilibrium occurs when the daughter has longer half-life than the parent. Eventually, when the parent activity is essentially zero here, okay, the remaining daughter activity decays with its own characteristic half-life. There is no attachment with the parent, so now it is by its own, okay, decaying by its own half-life. So parent decay, the daughter continued to decay after that. Iodine-131, which is the main therapeutic isotope in nuclear medicine, we talked about it, is the daughter in this decay chain. We see here the tellurium, iodine-131, had 30 hours, okay, half-life, while the daughter has 8 days. So the half-life of the daughter is greater than the half-life of the parent. It's a little bit complicated to understand this equilibrium, just to know that there are three situations of equilibrium. We have secular, transient equilibrium, and no equilibrium. In nuclear medicine, we are talking about transient equilibrium between the molybdenum and technetium. And this is important to understand because we'll come now when you use the generator, you need to understand this kind of equilibrium. When to elute your generator? We have generator in nuclear medicine to get technetium. So shall I elute it now? Elute it means that to get technetium from generator, we're going to explain that. So every how many hours I can elute the generator? Usually when we get the maximum activity when the daughter reaches to the parent here. So this is the maximum activity we can extract from the generator. We'll go through this one now. Okay. Let's talk about the properties of ideal radionuclide, what we want to have in nuclear medicine. The radionuclide should have half-life comparable to physiological study or imaging, hours to days. We don't need very short half-life. So if we inject the patient, the half-life is 1 minute, 2 minutes. So we cannot emit this kind of radionuclide because very short half-life. And we don't need very long half-life. We don't want to radioactive to remain or stay inside the body for a long time and expose the patient. So we need comparable, like good half-life, hours to days, it's acceptable. Readily available at reasonable cost. High specific activity, mean the ratio of radioactive to non-radioactive in the sample. We need it more radioactive than non-radioactive because non-radioactive isotopes has nothing. We need radioactive to be able to image that. We need radionuclides with good energy gamma emission for imaging and detection. We don't need too low energy. We need radionuclides that emit energy between almost, and for nuclear medicine, for gamma camera, between 50 and 400. Because if the energy of the photon emitted by the patient less than 50 keV, the photon will be attenuated inside the body. It will be absorbed by the body and will not reach to the detector outside, okay, because the energy is very less. So all the energy will be deposited inside the body, absorbed by the body, and this increases the patient dose without any benefit for imaging. While if the photon emitted by the radionuclide injected to the patient above 400 keV, so the same thing, the photon will escape from the body and also will escape from the detector, will not be stopped by the detector and detected. It's most of the photon will escape from the detector without any kind of recording. So we just expose the patient for high energy photon without any benefit to the imaging also. So we need reasonable energy. It is between 50 and 400. That's why we use technetium-99. It's about 140 keV, okay, and has very good half-life, 6 hours. We don't beta emission in our radionuclide. because it has no purpose in diagnostic imaging, because beta emission will be absorbed by the body and will not be imaged by the detector. We need good chemistry for radio labeling, and of course, non-toxic, biologen-free, sterilized, and so on. Any question before we go to radionuclide protection? Okay. Most of the naturally occurring radionuclides are very long life, like uranium-235, radium, whatever, and represent very heavy elements that are unimportant in metabolic or physiological process. So we cannot get uranium because it is the only natural. Sorry, can you repeat? Okay, we're going to repeat that, effective half-life. Okay, let me go quickly to effective half-life. Okay, we have, we say the half-life, it is the time required for the half of the atom in the radionuclide to decay. Okay, it's time, we have physical half-life, it is identity, it is characteristic for each radioisotope. It is the time taken for half of the atom in radioactive material to undergo decay. The physical half-life when isotope is related to the decay constant, and it's characteristic for every radionuclide. Okay, this is physical half-life. Like we said, technetium, 6 hours is fixed. We have also biological half-life, that the activity inside the body excreted in urine, in any liquid coming out from the body, in vomiting also sometimes we get out of the iodine-131. So the biological half-life affected by the uptake of the radionuclide within the body, inside the body. So we have biological half-life and we have physical half-life. Physical half-life is not changeable. Biological half-life, it can be estimated for each radionuclide. We can, iodine-131, for example, the half-life is 3 days. The biological half-life 3 days. Because we know that most of the uptake for iodine-131 will go to the thyroid, will remain in the thyroid for this amount of time. So we can estimate the biological half-life, but it's not very fixed. It's changeable according to the thyroid is hypo, whatever the function of the organ affect the biological half-life. The uptake of the radionuclide within the specific organ affect the biological half-life, but we can estimate that one. But physical half-life is fixed, 6 hours, 8 days, whatever. Okay, so when we calculate the effective half-life, we say how long the radionuclide will stay in the patient. We don't consider only physical half-life or biological half-life. We collect the effective half-life. There is a table for biological half-life for each radionuclide, and we get that one. What is the biological half-life for this radionuclide, and what is the physical half-life for this radionuclide, and calculated to get the effective half-life. And this way we can estimate how long the radionuclide material remain inside the body of the patient. Okay, did you get it? Okay. I don't see the comments here, sorry. It's not the matter of more accurate or some, it is the relationship between the physics. You have to consider the physics, the physical half-life and biological half-life to be accurate, to calculate accurately how long the material will stay inside the body. The effective half-life, it's just kind of relationship between the physical half-life and biological half-life. Okay, it is the relationship between both of them. So we have two half-life, biological and physical half-life, and the relationship between the physical and biological half-life, it can be calculated by calculating the effective half-life. Okay, thank you. I will go Bateman here. Okay. Okay, radionuclide production. We said that the radioactive material in the nature has very long half-life. So we cannot bring uranium and image the patient, get injected the patient in uranium and to image the patient. So it's millions of years of half-life. So the radionuclide used in modern nuclear medicine, all of them are artificial radioisotopes. It's not natural. Natural means very long half-life. So all the nuclear, technetium, iodine, whatever, it is all artificial. We made them. They are made by bombarding nuclide of stable atoms with subnuclear particles, such as a neutron and a proton, so as to cause nuclear reaction that convert stable nucleus into unstable radioactive one. So we have a stable nuclide. We just bombard or hit this stable with subatom. We have, for example, O18 stable. We just bombard this one with one proton and we get F18. Now it is unstable and we have different isotopes. So we create radioactive sources to use it in imaging by using the stable atom, and we use the subparticle like a neutron or a proton or electron, whatever, and convert the stable atom to unstable, to radioactive isotope to use it in imaging. Major ways of radionuclide production is reactors and accelerators. Reactors like nuclear reactor, accelerator, the example of accelerator is the cyclotron. It produces the positron emitters. The reactor, the beam particle is the neutron, the subatomic particle, a neutron. This neutron hits the stable atom and we get the radioisotopes, or there's another way. We will go in details now. Radionuclide produce a neutron rich because the beam particle is a neutron, so the resultant radionuclide will gonna have more neutron than a proton in reactor. In accelerator, it could be proton, neutrons, alpha particle, or heavy ion can be used in the accelerator. And the radionuclide produced gonna be like a proton rich or a neutron deficient, because mainly we use a proton, so the number of proton is more than the number of neutron the radionuclide produce. Delivery of radionuclides from cyclotron or reactor. So desired nuclide obtained directly from reactor accelerator via filtration process. So we can get the reactor produce radioisotope like iodine-131 is produced in the reactor. We can get this iodine-131 from reactor to the hospital and use it in the hospital. It has adequate half-life, so it can be transferred from one place to another, or can be transferred through the generator. So if we need to transfer the daughter which has short half-life, we put the parent in the generator, it has longer half-life, and move it in the generator, and we use the generator inside the hospital to get the daughter off from this generator. So we'll talk about this one later. So let's start with the accelerator, and the accelerator, example of accelerator is the cyclotron. The cyclotron is the most common accelerator used to produce radiopharmaceuticals for nuclear medicine, particularly for positron emission tomography, F18. The key components are, this is the cyclotron from above, and this is the side view of the cyclotron here. Okay, we have ion source. This is the ion source between the two Ds here. We have this. It provides the ions. Okay, this is the source of ions. The particles is going to hit the nucleus. We have magnets. It provides a magnetic field. We have two magnets here, up and down. These from D, because it's shaped. D here, we have two Ds. One D here and another D is here. These, it's hollow semicircular metal electrodes to contain the charged particle at the accelerate. Okay, we have AC voltage, accelerate the charged particle, and we have the target here where the stable atoms is waiting for the subparticle to interact and to get the radioisotopes. So to produce the desired radionuclide, a small packet of particles are generated in a burst from ion source here. Okay, this is the ion source. You create the particle. particle generated in this ion source. AC voltage applied, okay? Then particle accelerated into 1D of these two Ds. Inside the D, there's no electric field, but there's a magnetic field above and down, and this is called the circular path inside the cyclotron. When gap reach, this is the gap between the two Ds, okay, AC voltage switched from positive to negative just to accelerate the charged particle here. We have charged particle, just to get the charged particle created here in the ion and start moving. And this gap has AC. And this is AC converted from plus to minus. When a charged particle here, just to attract it going, for example, if we have minus particle, here it can become positive to attract it, then again change to negative to repulse it. It's just going plus and minus just to accelerate the charged particle inside the cyclotron, and the magnetic field keep this track. It's in a circular path. Each crossing of gap gives more 30 keV, so radius increase. We can see that every time the charged particle passes through this gap, this give more energy to the charged particle, about 30 keV, so the radius of the path increase every time, and so it's increasing and increasing and increasing until when the maximum radius achieved, particles are directed to the target. So the principle of the cyclotron is just accelerate the charged particle inside the cyclotron, keep accelerated just to gain more energy, just to prepare it to hit the target here and to produce the radioisotopes. Okay. The energy of the particle accelerating in the cyclotron is given in this equation. From this equation, we see that we want to use as light particle as possible. Just to see, this is the energy in MeV, and this is the magnetic field in Tesla. And we have R, the radius of the path. We have Z, the atomic mass of, the atomic number of the particle, and we have the mass number. And also by this equation, we can calculate the energy of the particle accelerated inside the cyclotron. So the mythical cyclotron had about 1.5 Tesla magnetic field, D diameter about 76 centimeter, a proton accelerated 15 MeV. So this is not fixed from one cyclotron to another cyclotron, is different. So this is the principle here of the cyclotron or any accelerator. So for example, if we have a proton, this is positive charge particle, hit the target, our target is O18. This is accelerated inside the cyclotron within the magnetic field and create the potential for this one until to reach to the target. Our target is O18. When a proton combined to O18, here we have 80 proton, 10 neutron. This O18 will be converted to F18 with 9 protons and 9 neutron. So 1 proton is added to this one. So now it is radioisotope, unstable element, can be used for imaging in positron imaging tomography. And always this follow with the neutron emission in accelerator. So always we have a neutron in the vault of the cyclotron. So this is the principle of the cyclotron. Charged particle hit the atom, make it isotopes, and use it for imaging. And this is some cyclotron produce radionuclide used in nuclear medicine. We have carbon 11, nitrogen 13, O15, F18, and we can see that how the decay mode of each one, all of them, like most of them emit by positron. Okay, and the most common one is F18 we use in positron emission tomography. The second radionuclide produced, the second kind of production is done by the nuclear reactor. Nuclear reactors operate on the principle of nuclear fission, the process in which a heavy atomic nucleus split into smaller fragments. So we have a neutron, its uranium nucleus inside the reactor. Okay, this uranium nucleus will be split into smaller nuclide and some more neutrons. This is the principle of a nuclear reactor. The neutron has the uranium nucleus. The uranium nucleus split into smaller fractions and neutrons. The nuclear fragments are in very excited state and emit neutrons. Okay, these neutrons will hit another uranium nuclide and produce another fission, another nucleus, and so on. So the emitted neutrons here. So this is the first one. A neutron hit the uranium nucleus. We get this uranium nucleus will be split into two parts, or not two parts, of course. It's smaller nuclei, many parts of that, and get more neutrons. These neutrons also hit more uranium nuclide, and the emitted neutrons may then cause new fissions, which in turn yield more neutrons, and so forth. It is sequence. Such a continuous self-sustaining series of fissions establish a controlled fission chain reaction. So this is a continuous kind of reaction. A neutron hit uranium, we get fission. This fission also produces another neutron. This neutron produce another fission, and so on. This is an example of this is the image of one of the nuclear reactor in Belgium. This is the core of nuclear reactor. It's contained. This is the component of the nuclear reactor core is, if we go one by one, the fuel cell here containing fissionable material, usually uranium-235. This is the blue one. This is the fuel cell inside the nuclear reactor, and it's surrounded by the moderator. And this moderator is to slow down the fission neutron. The slow neutrons, also called thermal neutrons, are more efficient initiators of additional fission events, commonly used moderator heavy water. Heavy water is reduce the energy of the neutron emitted by the uranium fuel. So we have uranium fuel here, and we have the moderator to reduce the energy of the neutron, because we need slow neutron that most effective to create more fissions. We have also control rods. This is the gray one here. The control rods contain strong neutron absorber material, okay? And are positioned to either expose or shield the fuel cell from another to control the chain reaction. So we can switch off the reaction by just apply this control rod above the fuel, above the uranium fuel, just to stop the reaction, or we can just take it off to start the reaction again. So this is the control rods, control the chain of the reaction inside the nuclear reactor. This is some of the example of nuclides produced in nuclear reactors. And the most important one for us is the iodine-131, is used for therapy and imaging. And we can see the reaction here that a neutron hit the telluride, and we get another here, the telluride 131 and gamma, then we get the iodine-131 by beta emission. So molybdenum-99 is made in one of two ways. Why we are talking about molybdenum-99? Because molybdenum-99 is the parent of technetium-99, the most common radionuclide used in nuclear medicine. There are two primary processes for producing molybdenum-99. Fission of uranium-235 and the neutron capture of molybdenum-98. So we'll go one by one. The fission of uranium-235, we said, okay, it produces a spectrum of fission products, including molybdenum-99. This isotope decay later into technetium. We said that the neutron in the reactor hit the uranium nucleus 235 and produce another fissions. So these fissions include molybdenum-99 and include also iodine-131, include xenon-133, cesium-137. Okay, so one of the fissions produced when the neutron hit the uranium-235 is molybdenum-99. Okay, this isotope is taken and put in the generator, and this used later to produce the technetium-99. This is the first method to produce molybdenum-99 by the fission of uranium-235. The second method is called a neutron capture, a neutron bombardment, or a neutron capture. Molybdenum-98, so the molybdenum-98 is inserted in the nuclear reactor core, okay? Molybdenum-98 target is introduced into the core of nuclear reactor where it undergoes a neutron capture to produce the desired molybdenum-99. So this molybdenum-98 inserted inside the nuclear reactor, then hit by or bombarded by the neutron. So molybdenum-98 converted to molybdenum-99, okay? And this is extracted from nuclear reactor and used later to produce the technetium-99. So two ways, the fission, the nuclear fission, and nuclear bombardment can produce the molybdenum-99. This is the pathway of the radionuclide generator of molybdenum-99 technetium. So this is the nuclear reactor. So here already processed uranium is irradiated with a neutron beam for 1 week in nuclear reactor. So this takes time, it's not just one hit. So for 1 week, the uranium is irradiated with a neutron, then we get the chemical, we get fissions, and we said part of the fissions will be molybdenum-99 and other isotopes. We get the molybdenum-99 and uranium together and separate the molybdenum from uranium by chemical way, okay? Then we get a pure, high purity solution of molybdenum after separated from uranium. And this molybdenum-99 capsulated, and this capsule inserted into the generator, and this generator shipped to the hospital to extract the technetium-99 and use it for the patient imaging. Okay. This is the decay scheme of molybdenum-99. Molybdenum-99 decay by beta, and the half-life of molybdenum-99 is 66 hours. Decay to technetium-99 metastable, then it transition, and the half-life of technetium-99, as we said, 6 hours, and it is from metastable to another more stable state, then decay again to ruthenium-99. In some cases, it is impractical to obtain enough of desired isotope directly from reactor or cyclotron. We cannot get technetium from reactor or from cyclotron because also it has short half-life. So we cannot move it from one city or one country to another. So we cannot get, for example, France produce technetium-99 for us and bring it from France to here. It's only 6 hours half-life, so we need a huge activity to just transfer to get the required activity here, for example, in Saudi Arabia. So the parent of the desired isotope, usually with longer half-life, is extracted by one of the production method already discussed. Then the daughter is chemically separated from parent in device known as generator. This is what we use in nuclear medicine. So parent has longer half-life. So we produce the parent like molybdenum-99 in nuclear reactor. Then the molybdenum-99, the parent, move it from the country, like from Canada, from South Africa, and bring it here to Saudi Arabia inside the generator. And the generator start eluting the generator to get the technetium-99, which has short half-life. So whenever radionuclide parent decay to another radioactive nuclide daughter, this is called the radionuclide generator. Several radionuclides used in nuclear medicine are produced by generator systems such as molybdenum-99, a production of technetium-99, and also we have germanium-68, also a production of gallium-68 used in positron emission tomography. The half-life of the parent is 67 hours or 2.7 days. It is for molybdenum, is adequate for transport and delivery. And the daughter has suitable half-life for patient investigation. So it's good to transport the parent, it has long half-life, and we have daughter has short half-life, it's good for imaging. And this is a schematic of the generator used in nuclear medicine, the molybdenum technetium generator. We have here a sterile vial containing cell line is placed into inlet line through the needle. And we have here evacuated to collect the technetium after eluting from the generator. And of course, it's shielded because the material here will be radioactive. And here we have the glass column contain alumina. And inside this alumina, there is molybdenum-99 absorbed. So molybdenum-99 here absorbed in alumina decayed to technetium-99 metastable. So the saline passes through this alumina column and extract the technetium-99 and go to evacuated vial here. And after that, we get this evacuated vial and use it as the perticnetate. We use it perticnetate, and we label this perticnetate with different chemical to get our radioisotope or radiopharmaceuticals, technetium-99 with MDB, with MEB, with DTBA, whatever. So normal saline evacuated vial, we just connect the evacuated vial and normal saline. They get the normal saline through the alumina, extract the technetium-99 from the molybdenum-99 here, and we get it in this vial and use it for the patient afterwards. So the technetium-99 elution means that extracting the technetium-99 from molybdenum-99 generator. Daughter activity build then decay at the same rate as parent. We are already discussed that in transit equilibrium. This is the parent is decaying, the daughter is built up, reach to the maximum here. At this time here, okay, maximum technetium activity reach after 24 hours. After 24 hours, we can extract the technetium, or we can milk the generator, we can see, or elute the generator to get the maximum activity. So we receive the generator on Sunday. On Monday, after 24 hours, we get the maximum activity from the generator of technetium. So after elution, the activity dropped down again. If we need the generator, for example, after 3 to 6 hours, we can elute the generator again, but with less amount of elution. We get about 40% after around 6 hours. Still, we can have some activity if we have more patients. So after 18 hours, like next day, after 18 hours, we can get activity only less than 10%. We can get almost 90% of the initial activity. So the activity is reduced every day. So the generator is enough for 1 week or maximum 2 weeks for one facility. So every week we have to change in our facility in King Fahd Specialist Hospital. Every week we have one generator because we have high number of patients. Every week we change the generator. We receive the generator on Sunday. On Monday we use the first elution, and the activity will be the highest, the maximum for example, on Monday morning. After we get the technetium from generator, we label this technetium with different compounds and use it for the patient. There are potential issues with generator we need to be aware of. The first one is moly or molybdenum breakthrough and alumina ion breakthrough. So during the extraction of technetium from generator, we say that molybdenum-99 decay to technetium, and the normal saline extract the technetium-99 from molybdenum. But still, molybdenum-99 sometimes go with the saline and go to our vial. So inside that vial of the technetium, still we have some of molybdenum-99. This molybdenum-99 is not useful for imaging agent, has own emission. The energy is 704 keV. It's very high energy. We don't need it for the patient, and it's not useful for imaging. Okay. Any question here? I don't know. I don't see. Okay, so to detect this molybdenum-99, we have to use thin, in the dose calibrator, we use lead shield that prevent 140 keV of the technetium. So all the 140 keV of the technetium will be absorbed by this vial shield, and we get only the radiation from molybdenum-99 in the dose calibrator. So there's a way to measure the molybdenum-99 by dose calibrator and see how much molybdenum inside our vial. Okay, and we have a specific amount of molybdenum. Beyond this amount, we cannot use the technetium because it will be very high energy and it will affect the patient imaging also. Another issue is the alumina ion breakthrough. can interfere with the labeling process and can cause a clumping of radioblasts cells. So alumina, because we have alumina column inside the generator, some alumina atoms will go through the saline and go to our vial also. And this can be detected by chemical tests. We can see how much alumina inside, and beyond specific amount, we cannot use our technetium. This is some of radionuclide used in the nuclear medicine department. We have about 20 radionuclides, but we have hundreds of labeled compounds. So technetium can be labeled with tens of compounds, as we say, technetium 99, DTBA, maybe whatever, HMPO, and so on. And this is, as we say, this is a clinical nuclear medicine procedure. You can read it by yourself here. What can MDB for bone scan, and we can MAG3 for renal, and so on. Let's go for a question and have a break after that. The ideal radiopharmaceutical would have all the following except what? Long half-life, good chemistry, energy between 150 to 150, and high specific energy activity. Good. A is long half-life. We don't need long half-life to remain in the body. All of the following are positron emitter used in PET scanner except CO15. O15 is produced in cyclotron, and also it's PET, it's used in PET. So carbon 11 is used in PET. O15 is used, produced in cyclotron, and again, this ammonia, nitrogen 13, only the boron 19 is a beta emitter and is not used in PET. Which of the following is produced in cyclotron? Yes. We know F18 is the cyclotron products. Cesium-137 produced in nuclear reactor. This is iridium-92 produced again in nuclear reactors. This is the potassium-40 is a natural radioactive isotope of potassium. Okay, this is natural, it's not produced. These two reactors, and this is cyclotron one. After 10 half-life, the factor of activity remaining depends on the initial activity, 1/10, 1/10 squared, 1/2, 10 times. After half-lives, after 10 half-lives, sorry. Okay, D. Excellent. So the answer is D. The activity remaining after 1 half-life is half. After 2 half-life, we have 2 half-life, half-life 2, and so on. So the remaining activity is half to the power n, number of half-life. After 24 hours, the activity of 100 megabecquerel of iodine 123 T half is 13 hours. Source will be about how much the final activity. The initial activity was 100 megabecquerel. After 24 hours, how much the activity if the half-life is 13 hours? You can estimate it like approximately. B. A. We have different answers here. Okay, let's analyze the question here. The half-life is 13 hours. So after 24 hours, we have almost 2 half-lives. 26, almost 2 half-lives. So the first half-life, 100 becomes 50. Second half-life, 50 becomes 25. So the answer is B. It's approximately 25 megabecquerel. It's almost 2 half-life, 24 hours. So in this way, we can calculate, just give estimation, how many half-lives, okay? So we can get this one. So we have 2 almost half-life, we get 25 megabecquerel. Any questions? I know it is like somehow it's confusing the radionuclide production, because if I want to go for radionuclide production in details, it's going to be one presentation or one course for cyclotron, one course for nuclear reactor. So that's why I try to give you 1-2 slides for each one, try to put everything. It's not easy to deliver the information for radionuclide production. It is a huge material, cannot explain it in 1 or 2 slides. Just to have an idea, what is the nuclear reactor? It's coming from fission. Cyclotron accelerate the charged particle inside the cyclotron. What is the difference between nuclear reactor and cyclotron? And the molybdenum produced in the reactor 2 ways, like by fission, and one part of the fission will be molybdenum 99. We take it off and they produce technetium 99, or by the neutron capture, we put the molybdenum 98, capture one neutron, becomes a neutron, a molybdenum 99, and we extract the molybdenum 99, put it in the generator, and so on. This is what I need you to know about the nuclear reactor and cyclotron. Otherwise, it is a huge material. We cannot cover it into a slide. That's why it became a little bit confused, and they didn't go into details with the radionuclide production. Otherwise, if you have any question, please let me know before. If you want to have a break or to continue, let me know.
ممتاز.
أستاذ محمد بناخذ بريك أتوقع. كم ساعة الحين؟
اوكي، الساعة 11:15 تقريبا الحين.
ايوه.
كيف دكتورة مريم؟
حلو. لو أخذنا بريك الحين، ويعني إلى لأنه بتجينا كمان وقت صلاة الظهر والغداء، بس لو أخذنا الحين لين صلاة الظهر حلو. أستاذ محمود، كم باقي لنا محاضرة قبل الغداء؟
والله هاي الحين خلصنا محاضرتين، أنا عندي حوالي 7 ل 8 محاضرات، فيعني لسه كثير.
طيب حلو. أجل نصير ناخذ ربع ساعة الحين شوية، وبعدين نرجع نشوف كيف الأمور.
إيه، خلينا نخلص راديشن ديتكتورز بعدين نروح على الغداء
أيوة تمام. لأن المحاضرة الجاية يمكن أقصر من
بعدين ندخل بالجاما كاميرا والشغلات الثانية. نخلص راديشن ديتكتور.
يلا ربع ساعة يا جماعة.
بعدها.
أيوة ربع ساعة وحياكم.
نرجع على 11:30 إن شاء الله.
إن شاء الله.
يعطيكم العافية.